So the method that we use to determine stability in an op-amp is what we call the Nyquist stability requirement. So let's look at the transfer function for our closed loop gain in our op-amp. So we have A of S is equal to little a of S divided by 1 plus T of S, where T of S is equal to little a of S times beta, our feedback factor. So we would say that the system is unstable if A of S went to infinity. So looking at our transfer function, how can our system go to infinity? Well, if T of S was equal to minus 1, then we would have little a of S divided by 1 minus 1, which is equal to infinity. We should also note that if the denominator is negative, we're also unstable. That would be equivalent to having a pole in the right half plane. So what we're looking for is if A of S times beta, the magnitude is greater than or equal to 1 when the angle of A of S times beta is equal to exactly minus 180 degrees. This would create the condition where our denominator blew up, went to 0, and our response blew up towards infinity. And this criteria is called the Nyquist criteria. And essentially what it's saying is that since we're already configuring the operational amplifier in negative feedback, we already have 180 degrees. If we get an additional 180 degrees of phase shift from our loop gain, the feedback to the input of the amplifier would become positive, and we would have a positive feedback system, and we know that positive feedback systems are unstable. All right, so let's look at the stability of a feedback circuit using a single pole op-amp. So what we're going to say is that our operational amplifier has a single pole response. In other words, little a of S is equal to A sub 0, some DC gain, divided by 1 minus S over omega P1. We've got one pole in our system. This is the open loop transfer function for our op-amp. If we configure this in a closed loop, we know that our gain was A of S is equal to little a of S divided by 1 plus little a of S times beta, which is equal to A sub 0 divided by 1 plus A sub 0 times beta. This is our DC loop. This is our DC closed loop gain. And it's multiplied by a frequency shaping factor, 1 divided by 1 minus S divided by omega P1 times 1 plus the loop gain, the DC loop gain, A sub 0 times beta. Now we might label this term A sub 0 times beta T sub 0, the DC loop gain. So T sub 0 is our DC loop gain. T of S is our AC loop gain. So next we're going to look at how to use a Bode plot to determine stability.